Modern national air defense systems are engineering marvels, funded by billions. Yet, under the weight of organized asymmetric attacks, these massive shields can completely collapse. When these systems fail to protect their airspace, the standard public explanation is simple logistics. The defenders ran out of interceptor missiles. This assumes a simple math problem of supply and demand. But the exhaustion of ammunition is merely a symptom of a much deeper structural vulnerability. A defense umbrella is an interconnected network of early warning radars and interceptor batteries, synchronized to engage threats in real time. When this shield falls, it isn't a logistical glitch. The grid is deliberately dismantled, piece by piece, to trigger a systemic collapse. Professor Ted Postol, a physical and military analyst, has documented the specific mechanics behind this type of defense breakdown. His analysis reveals that the collapse of a high-tier defense grid follows an intentional, mathematical sequence dictated by the attacking force. This sequence relies on three specific operational steps: forcing the attrition of defensive interceptors, destroying the critical tracking radars, and exploiting airspace with mass-produced drones. This specific order of operations is engineered to isolate the defender's most expensive hardware and render it completely useless. By adhering strictly to this model, an attacker strips away heavily funded defenses entirely, ensuring unmitigated penetration into the target airspace. The sequence begins with Phase 1, the attrition trap. An attacking force launches waves of older, obsolete ballistic missiles toward the target. These aging weapons are mechanically flawed. They fly on unstable trajectories and frequently break apart at high altitudes long before they reach their intended coordinates. Even if the warheads make it to the ground, they are highly unreliable. Observation of these attacks often shows a lack of visible horizon flashes, meaning the payloads fail to detonate upon impact. But dealing physical damage is not the objective here. These flawed weapons are deployed specifically to act as a mathematical sponge for the defense grid. The defense system operates on strict protocols. When it detects incoming ballistic arcs, it must automatically launch its highly advanced, limited supply of interceptors to meet them, regardless of the incoming weapon's actual reliability. This creates an extreme economic and logistical disparity. The attacker spends cheap, expendable munitions, draining the inventory of interceptors that cost millions of dollars apiece to manufacture and are vastly harder to replace. Phase 1 successfully engineers an unsolvable logistical deficit. With the primary magazine depleted, the defender is left vulnerable to the actual primary objective of the campaign. This brings us to Phase 2, the systematic targeting and destruction of early warning and missile defense radar bases. This step relies on a foundational rule of aerospace engagement. Without active radar tracking, an air defense system simply does not exist. The network relies entirely on large, stationary radar arrays. These massive structures form the backbone of the defensive grid, and they are completely unarmored. When these arrays are shattered, the critical sensor-shooter loop is instantly severed. At this exact moment, an interceptor, no matter its speed, payload, or unit cost, becomes functionally inert. Without a radar base to provide targeting data, the missile cannot observe or track incoming threats. Professor Postol notes that executing this step is the single most important tactical move in the entire war sequence. The public tends to fixate on the interceptor missiles themselves, tracking how many are fired or kept in reserve. But the reality is that severing the sensor loop collapses the entire architecture. Once the radars are gone, all remaining munitions and all previous financial investments are neutralized. With the radars destroyed, the attacker initiates the final phase, deploying mass-produced asymmetric drones directly into the newly blinded airspace. Compared to traditional cruise or ballistic missiles, these drones carry an extraordinarily low manufacturing cost. This extreme economic efficiency allows an attacker to scale up manufacturing indefinitely, producing overwhelming volumes of weapons for a fraction of the cost. Physically, these weapons are built using highly interchangeable universal components, completely removing the bottleneck of specialized military-grade manufacturing. Despite their inexpensive construction, these drones execute severe terminal accuracy. Their flight paths can be programmed from thousands of kilometers away, navigating complex routes over long durations. As they enter the final homing phase, they have the ability to optically scan and verify their specific targets before impact, ensuring precise strikes on critical infrastructure. Combining extreme manufacturing volume with severe terminal accuracy permanently upends the traditional economic balance of air defense. The defender can no longer afford the math required to survive. To understand why this is fatal, we look at this split-screen comparative chart. A healthy defense system operates on a 1-to-1 ratio, but a radar-depleted system now faces a ratio of 1 interceptor to hundreds of incoming targets. Postol points out an essential physical distinction. From a purely aerodynamic standpoint, these drones are relatively slow and easy for an interceptor to hit. But that physical vulnerability is irrelevant. Trying to intercept this sheer volume without active tracking radar is a mathematical impossibility. In this degraded environment, drone swarms maneuver through the target airspace with total impunity. The massive, rigid infrastructure of the high-tech defense network is entirely circumvented by the agile, highly disposable nature of the attacking swarm. The attacker has successfully executed an asymmetric inversion. The defender's reliance on incredibly complex, expensive technology has been turned into a fatal liability. If we synthesize this sequence, we get a clear timeline of failure. This chart plots 3 overlapping metrics: interceptor inventory crashing in Phase 1, radar capacity dropping sharply to 0 in Phase 2, triggering an exponential spike in drone volume during Phase 3. The precise moment radar capacity hits 0 is the direct trigger allowing the drone volume to escalate uncontested. The final equation for systemic collapse is rigid: sensors destroyed plus interceptors exhausted plus massive asymmetric volume. The result of this equation is unmitigated target penetration. The air defense network was not overpowered by a superior individual piece of technology. It was completely outdesigned operationally. What follows this structural collapse is the severe, unchecked degradation of general military and logistical capabilities on the ground. This model of failure is not unique to a specific conflict or a single nation. It applies to any modern, advanced air defense grid facing a disciplined, heavily resourced attrition strategy. This exposes a critical flaw in current defense philosophies, forcing a reevaluation of how massive networks are designed and funded. Professor Postol's analytical model leaves us with a stark strategic reality. Once the radar architecture is lost, the protection once provided by expensive high-tech shields vanishes, ceding total control of the airspace to cheap, programmable weapons.